Hello. Okay. I have no idea what I'm gonna do. um, so I know what I want to try to do. As a recap, last time we proved that a differentiable function in a proper domain, which we had defined using a certain sort of, it's a locally convex, has no isolated points, and it has some other property where it's sort of wide in the sense of we have some loops that we can sort of circle around any point. So last time we had shown that if we have a differentiable function in a set like that, then it's actually analytic. That has a power series at any point which converges in a neighborhood. So that was last time. We also sort of investigated some novelties. So especially we had this was one of the ones that we had covered. I edited these a little bit over the weekend, so they flow a little more nicely. But we had, like, this was sort of an interesting little piece that we had proven. I don't think this is useful at all. It's just kind of interesting. It's the kind of thing that would be really hard to prove without our machinery, despite being apparently useless. It is the kind of thing that anyway, so so that's what we had done before. Okay, so we also had this for some exponents. We might use these. Actually, we're going to use this a little later. Maybe not in this power series in particular, but this extended exponent function later down the line. Anyway, our current goal is we want to prove a certain form of inverse function theorem or open mapping theorem. So I'll start sort of a draft of the theorem we want to prove. Let me get down here. So the weakest possible version that we could prove is let f map. We can say let alpha be a sequence of coefficients in n0 and f map x to the sum of x power n alpha sub n. Actually, we can say let alpha be this and phi alpha less than infinity, and f be defined this way, with alpha 1 non-zero. Actually, we can say alpha 1 in a star. So we want to say something along these lines. This is maybe not exactly how we're going to word this theorem in the end, but roughly we want to say, in the most general terms, we want to say, let's have f defined by this power series, which has a non-zero radius of convergence, and we're going to say its derivative at at the center point. So here we're just saying the simplified case. Our center point is 0. So we're saying its derivative is a unit. So it's a alpha 1. That's the derivative of f at 0. Alpha 1 is a unit. If this is the case, we want to say there's a function g analytic in the neighborhood of f of 0 having g of f of x equal x. So g is an analytic inverse function for f. That's what we want to try to say. So roughly we want to say if we have a function which is analytic and its inverse function, or sorry, and its derivative is a unit, then we want to say that the function has a local inverse function. There's definitely some ways we can strengthen this. So for example, we don't have to require f to be a power series. So right away we could simplify this to say, you know, let, instead of saying all these things, we could say let f map x to, actually we can just say let f map s to a be analytic at x0 in a, sorry, in S. I'm going to say analytic in S. Let's actually say S is a proper domain, because that implicitly tells us that the radius of convergence is non-zero. And for some x0 and S, we have f prime at x0 is in A star, then f, then there is a function g analytic in a neighborhood of f0 having g of f of x equals x, right? Yeah, so this is sort of essentially what we want to say. This one is actually probably going to be a lot easier. Because we've said f is analytic in a proper domain, we can essentially assume that f has a power series, and then just find an inverse function for that power series. Okay, so I guess we can try to prove this one. There's also the more difficult inverse function theorem. So the way that's normally phrased, let's see that. The way it's normally phrased is actually, it doesn't require the function to be analytic. So here we have f is continuously differentiable with a non-zero derivative. So here, instead of having non-zero derivative, we're actually saying our derivative is a unit. So a non-zero unit derivative at a point A, then f is invertible in a neighborhood of A, and the inverse is continuously differentiable. And the derivative of the inverse function at b equals f of A is the reciprocal of the derivative of f at A. Okay. So this is the normal inverse function theorem. So it's saying we have a continuously differentiable function with a unit, a derivative which is a unit. Then it has an inverse function which is continuously differentiable. So we can try to look this is interesting. An alternate version assumes that f is continuous and injective and differentiable at a instead of continuously differentiable. So there's a lot of different ways that this function can be proven. Okay, so it doesn't have to be continuously differentiable. That's good. That's the most general form. So the idea I have for for dealing with the analytic case with positive radius of convergence, the idea that I have for this is essentially, I'm just going to work out what the inverse function should be, prove that it converges in a neighborhood, and then verify that the inverse actually applies. I don't know if that's a good idea. I don't know if that's a good idea. That was one of the ideas I had. So here's the standard proof. It involves a lot of absolute values, which we don't normally have, and bounding things. So let's see. Basic idea is to prove a fixed point theorem using the contraction mapping theorem. Interesting. Okay. Taking derivatives, it follows that okay, interesting. So it looks like what they're doing is they're saying, take this function as a function of t, and rewrite this using this integral, and then you can bound its difference, which would be this, by the supremum of its derivative, essentially. So we can do something similar to this. But then it wants us to say choose delta greater than 0, so that so on and so forth. So they're saying find a neighborhood of x where this difference, f of x minus I, stays small. That's maybe something we can't do. Although, okay, I have a really weird idea that might work. Okay. We would definitely want locally convex. That's always one that's, in order to do anything like this, we're gonna need locally convex. Although actually, yes, right. So right here, we're going from x to x prime using a convex sum inside of f. So we want f to be defined on a locally convex set, I think. Okay, so let's try that. So we'll say let f map s to a be, actually we'll say let s be a subset to a b locally convex, and f map s to a be differentiable. Actually, we want to say continuously differentiable. Then we want to say, let's see, what do we want to say? So we're gonna have to figure out okay, I think what we wanted to say is how does this proceed? Probably what we want to say is we want to end up saying there's a function g which is continuously differentiable on the image of f. So we can say then we would say then there is a neighborhood. I will say f of, actually let's do this, let's do x0 in s subset to a be locally convex, continuously differentiable. There's a neighborhood f of x 0 in u subset f, the image f of s, and a function g mapping u to a continuously differentiable g with f, or we're going to say g of f of x equaling x for all x in some neighborhood of x0, I think. Isn't that what it is? Hold on. G define near this with g of f. Yeah, that is what this standard theorem is framed as. Okay, this seems reasonable. By the way, if you would like, I don't know if this is useful at all, we could look at my original theorem for proving what we're trying to prove now is more general than what I had proven previously. what I had proven previously in my previous draft, I had only proven it for analytic functions. Analytic functions in an open set, specifically. Open sets are, in the context of A, open sets are actually really restrictive. There's not very many of them. I had mentioned this before, but every open set is unbounded. In fact, every open set is unbounded on infinitely many directions. So we have countably infinitely many sort of basis vectors. Any open set is unbounded in infinitely many of those. That's just a consequence of the product topology. That in a product topology, the open sets are generated by having a finite product of open sets. So it would be, they call them cylinder sets. I guess I don't want to get into it too much because that would be distracting. But the original theorem I had it's just defined for analytic functions on an open set. If we this theorem, analytic functions on an open set, this applies to all power series with positive radius of convergence. Not this one, it's actually down. It's a really gross theorem. It's here. This whole nasty theorem. So the original theorem applies only to analytic functions in an open set. But we want continuously differentiable functions in a locally convex set. That's sort of an improvement on the other one, because not all continuously differentiable functions in our space will actually be analytic. We know that if they're continuously differentiable in a proper domain, then they will be analytic. But proper domains they're sort of analogous to a complex domain in that you can surround it by a loop that sort of goes in a full circle. Its projection onto the complex plane goes in a full circle. Domains that are too thin won't have that property, so that will sometimes fail. Actually, sorry, this should be, I'm missing the derivative condition. Okay, so let's see. I have a really interesting possible approach to this, to doing this. So, okay. But let me just read and understand this first. So, okay. So they're saying that this difference, f of x minus f prime minus x plus x prime, is bounded by this, which is this times the supremum of this thing, and then choosing delta so that this difference, f prime x minus I, so that would be this supremum bit. Choose delta so that choose a neighborhood so that when x is within this neighborhood we have this difference. Suppose that the norm of y less than delta onto, suppose that y is in this other neighborhood, and define x in it inductively using, oh, fascinating, add y and then subtract f of x sub n The assumptions show that if x and x prime are below delta, then we have this minus that is bounded by this divided by 2. Okay. In particular, f of x equals f of x prime implies x equals x prime. Okay, so they're right through here. They're showing that there is a neighborhood on which the function is injective. That's the first thing they've shown. So all of this, I think, all of this is just showing that the function is locally injective. So there's a neighborhood. This is actually really interesting. This should be way easier than what they're doing. If that is if all they're doing is they're just proving this, then actually this result is really easy. You don't need all of this. It's basically an immediate consequence of f prime being non-zero. But okay. In some neighborhood. Okay, so they're saying in the inductive scheme, so that's this, they're saying that each one of these xn's are also going to be in this neighborhood, and this difference is going to be bounded by delta on 2 to the n. I'm not sure where they get this from, but okay. But what are they using this for? Xn is a Cauchy sequence tending at x. By contraction, f of x equals y. Check that g equals f inverse is c1. Where did they even get g from? Hold on. If it's a c1 vector value function on an open set, then the determinant is non-zero if and only if there's a c1 g with this and this. Oh, okay. Okay, so they're starting with this. They're just taking this as a premise. This whole piece. So right out the gate, they already have this g function, which is if f is a c1, so a continuously differentiable function with a non-zero derivative, then there exists this function g defined near this point, where g is the left inverse and a right inverse locally. So they're already starting with an inverse function, actually. So this proof does not establish the existence of the inverse function. Okay. In that case, we'll have to prove that separately, I think. So I do know how we can do that. I think I have an idea. We can say let f map s to a be continuously differentiable with f prime and x0 and s have f prime at x0 is non-zero, then I can say how would we frame this exactly? there's a function. Oh, they already have their function being C1. Wait, what? Isn't that the entire point? Oh, maybe I'm dumb. Oh my gosh. Where did they get the function g from, though? Okay. So what there's... Okay. So... Okay, I was right the first time. They just went a little fast. So this section is proving, or at least it seems like they're trying to prove, that f is locally injective. It's not clear that that's what they've done. It isn't clear that that's how that has occurred. This is actually really poorly written. Okay. Wow, this doesn't help me at all. Okay. Let's see if I can find a better written proof. This is extremely hard to follow. It's unclear where they actually start the proof. Actually, so I'll leave that open there. I'm sure this is probably going to be quality if this is a textbook. I can't read Chinese. Hopefully, okay, it seems fine. Okay, so let's see, universal theorem, blah blah blah. You got a proof for this one? There is not a proof. Wait, hold on. This is an extremely long lemma. Nope. Okay. All they've done is just give some example. They just stated it without proof. This bothers me. Yeah, so I'm trying to understand this proof. So the problem that I'm having understanding this proof is they start by saying the inverse summation theorem states that f is a blah 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 if and only if there is a C1 G blah blah blah, so on and so forth. This is proven by this and that and so on. And then by derivatives, you can just prove what the derivative, using the chain rule, you can prove that the derivative of the inverse has to be the reciprocal of the original function. Okay, so like this is fine. The problem is that it's unclear where they actually start the proof. Chain rule implies f prime a, f prime b, right? Chain inverses. Wait a second. Okay, now I understand. Their points are a and b. That's their points. They haven't said where x and x prime come from. They just sort of pulled them out of thin air. They haven't said where x and x prime are. They just sort of are there. I'm assuming that x is x is near A and y is near B. So x and x prime are both quote unquote near A. Okay. So they're going to say they're going to take this case where A and B are 0. Okay, I understand. And they're also going to do a transformation to assume that the derivative of f is 1, the identity matrix. They're doing the vector theorem. I'm just going to ignore the vectorness. Yeah. So they're taking this assumption that the derivative is the identity, and A and B are 0. Okay. So this is all they've done is they've just made this a little easier by assuming A and B are 0 and the derivative is the identity. This section here is proving, yes, all of this section, this part here, they're proving, this part proves that f is locally invertible. So they're saying if we have these 2 points, f is continuously differentiable, then there's a neighborhood under which if f of x equals f of x prime, then x equals x prime. So that's invertible. That does immediately imply the existence of a local inverse function. So just by getting this, by having this locally injective property, they do have a local inverse. And then they just have to prove that this local inverse is continuously differentiable. So first they prove that it's locally injective, and that gives you the inverse. And then they prove it's C1. Once you have that at C1, you do get this derivative property right here, this one down here, that the derivative of the inverse is the inverse of the derivative, the multiplicative inverse. The functional inverse of the inverse, the derivative of the functional inverse is the multiplicative inverse of the derivative of the function. Okay, so this is fine. We can do this part on our own. I think this is something that we can probably do. Maybe not using exactly the method that they used. Actually, doing this method would probably be viable. But we'll see if that's necessary. I think we can actually maybe exclude the condition of being defined in a locally convex set. I think we can actually do that. So okay, so we're going to say let f be map S to A be continuously differentiable. Then actually I'll do it this way. In order to prove the locally injective condition, I think we will actually prove, I'm actually going to prove, I was thinking that I would probably have to do this, but we have this, in the old draft, we have this stronger version of taking a derivative. I'm going to prove that, if possible. Okay, so let's put it, oh, maybe we will have to have it locally convex anyway. Yeah, to assure that the difference equation exists. Okay. Actually, let's just do convex, because that'll make it easier on us. Okay, so I'm going to prove that if we have a continuously differentiable function in a convex set, I want to prove that we can calculate it using this derivative. So for the next theorem, okay. So we're just going to say, let's see if I can fix this. No, I think I like this other one better. Missing parentheses. Where? Hold on. That doesn't make sense. It does think this is... What's wrong about this? Oh, that's why. Okay, so what we're introducing for this notation, for this next theorem, is we're saying we're going to use a shorthand for taking, so we have a limit of a function g, which maps a squared to a, and we're taking this limit over ab limiting to xx using the subspace topology of this subspace of a squared, which is the set of a, b, such that a is not equal to b. And we denote this as the limit as a not equal b going to x of gab. So we're just going to sort of use this notation as a shorthand. And the way that we're going to use this in this theorem is we'll say, let S subset A be convex, and F map S to A be continuously differentiable. Then, and the result is this. We want to, the conclusion is that we want to be able to calculate f prime at any point x using this limit scheme. So this is sort of a more restrictive type of derivative. So this is sort of the one that we've been talking about occasionally. That instead of just taking one of these variables tending to x, we can take both of them. And so the proof is, so we'll first start off by saying, since f is differentiable in the convex set S, then the difference quotient is always defined as per, and then we'll have a reference here. And to make this reference valid, we're going to have to go up here and tag one of our theorems. So the theorem that we're using here is a little higher up. Yes. No. This is integration, I think. Yeah, this is integration. It should be around the derivative section. It's actually, I think, our last theorem of the derivative section. Yes, right here. So right here, I'm going to tag this theorem, actually label it using this label. And that made it look really not good. Okay, so let's see. So pop down here. Okay, nice. So we've referenced this theorem. So this theorem 3.10, we had proven that if we have a function differentiable in a convex set, then we can always take the difference quotient, for any 2 points. So that's the first part. Now we just have to prove that it converges. So we could say okay, so in order to prove, so we know that this difference quotient always exists. To prove that it converges to f prime of x by we're going to prove it by contradiction. Suppose it does not, then we can find a sequence. We'll do a sub n, b sub n, going to x, such having a sub n not equal to b sub n, and this fraction f of a sub n minus b sub, f at b sub n divided by a sub n minus b sub n does not go to f prime at x. Okay. So we're going to say, so by contradiction, suppose it doesn't, we've had this sequence. So we have a sub n and b sub n not equal, and this difference quotient does not tend to f prime at x. In order to prove our contradiction, what we want to do is we want to say let's think on this one. How are we going to do this? I think we probably want I'm just trying to figure out how we're gonna do this one. Let me also give me some space here so that I can see everything that we're looking at. Maybe there's some way actually. Okay, we might want to try to cut it into two different sort of pieces. I don't MS Paint. Okay, so what I'm trying to think of is we have our point here. We'll say this is x, and we'll say we have some points A and B, and this line between them is sort of representing. This is sort of the line we're going across to calculate this difference quotient. I'm trying to think if it's possible to utilize actually a triangle like this in some way. I'm not entirely sure how this would be useful. But we do sort of need to incorporate this sort of we need to somehow relate these difference quotients to the derivatives near x in some way. We could say Oh wait, maybe, okay, I have an idea. We can actually use mean value theorem, I think, in a really particular way. What we can do, I think, is we can use mean value theorem to show that the if we take this difference quotient, there should be some point on the line where, for example, the real part of some nth projection is the same as one of the derivatives on the line. That's kind of what I want to say. I don't know if that's, let me think. Because essentially we have to result in saying that f is not continuously differentiable if we're doing it by contradiction. That essentially has to be, we have to say if we have this sequence, then we should have f not being continuously differentiable. So something about these difference quotients has to be. Oh, let's do it this way. We can say okay, so we have the sequence, and we can say we want to say that this yeah, okay. Why is it XX? X is a point in S, which is a subset of A, and A comma B is a point in A squared. So we want both AN and BN to go to X. I could also rewrite these. Instead of saying A sequence, we can say we can find sequences, and it would be A and BN, which go to X. So each of A and Bn are going to X. That's essentially the idea. Let's actually call this, let's give this a label. Actually, I'll use lowercase delta for some reason. Okay, so we could try something like this. So if we have this sequence not tending to f prime at x, then we can need this difference. So this difference quotient. We could consider this as one of the difference quotients for the standard derivative at b sub n. So if we subtract f prime at b sub m, if this tended to 0, then because f prime at b sub m, f is continuously differentiable, so this f prime at b sub m has to tend to f prime at x. So this difference does not tend to 0 is what we're saying. If that's the case, then we can say I think this is actually this proof would be uniform differentiability. It's actually what we're attempting to prove. Actually, I'm pretty sure those are equivalent. Uniformly differentiable if and only if it is continuously differentiable. Yes. So that is actually what we want to prove. That's actually what we would be doing if we approached it from this direction. So if we're trying to say that this difference quotient minus f prime at b sub n, if this doesn't tend to 0, then actually what we want to say is that this, as we take our a sub n's closer to these points, that they won't converge uniformly. So actually we could try to prove it another way. We could try to prove that if a function is continuously differentiable, then its derivative is uniformly differentiable over a compact set, or something to that extent. How would we do that? We could attempt to use the boundedness. So continuous functions are bounded on a compact set. So f prime of b sub n is it. No, that wouldn't help exactly. Maybe we can use integration. Let's try that actually. We'll attempt to use. So we have. Actually, yeah. Let's do it that way. Okay. So in integration, way up here, a little higher. Okay. In our integration section, so we have a continuously differentiable function on a convex set. That means so here, actually. What we had as one of our results, if we have a function which is locally convex and simply connected, which is true of a convex set, and then a differentiable function has an antiderivative. So actually we can maybe use this. Let's actually try that. So we actually have an antiderivative. So let's see. So let's go back up here. So we do have an antiderivative. Okay, so since f is differentiable into convex set S, as per this theorem, difference quotient for f is always defined. We can also say, moreover, we can also find an antiderivative, and we want to say if f. Oh, okay. Let's do it this way. F is continuously differentiable in the convex set S, then let's actually find that. We want to say the integral of, okay. F is blah blah blah, for sure. Okay, so F is, right, okay, so we'll do it this way. So differential underlies to S, this define, we just put that F prime of X. Okay, so we have these sequences, and suppose that, and the difference, this delta difference, the difference quotient is not in F prime of X. Then we could say, since F is an anti-derivative for the continuous F prime, we have, that's what I'll say, F, actually let's just do it this way, F at A minus F at B, B sub n, A sub n. This is just this integral from A sub n to B sub n of F prime at X dx. Actually, not, we don't want to use X, because we've done that already. Let's use a different variable. Let's use, I don't know, we'll just use y in the integral, it doesn't matter. Okay. F is an antiderivative for the continuous F prime. It is also an indefinite integral function. So then we have this, is that, which is, we can do the substitution. F prime, we're going to do A sub n plus t B sub n minus A sub n dt. Okay, so we're going to use this integral. So essentially we've just used the substitution rule. So we're saying f is an antiderivative for its derivative, obviously. Its derivative is continuous and thus integrable. So its antiderivative, which would be f, is also an indefinite integral function. So essentially this is just our fundamental theorem of calculus. F at an minus f at bn is equal to this, which is equal to this, by using the substitution rule. So if I also, we can divide now f at an minus f at bn divided by an minus bn. We can divide by an minus bn, and we just get this integral. I feel like we've done this proof before. I'm pretty sure this is exactly the setup we had used. It was in the integration somewhere. Yes. This is exactly the same proof that we used to prove that if we have a continuous function, its indefinite, each indefinite integral is an antiderivative. So its antiderivative is continuously differentiable to this function f. We've literally just repeated this exact setup. That's nice. So actually we can probably adapt this proof. I'll leave this here for now, but I'll keep this in mind. We can probably adapt this proof and actually merge it with our other, the proof that we're working on right now. Yeah. I think that's good. That means I'm on the right track. I'm pretty sure this is going to work out because actually what I wanted to do next is exactly the same. Which is, so f is blah, 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 we have this integration. Okay, and then we can say, and let me align these up right now. I'm going to do ampersand, ampersand. Okay, so you've got this difference quotient, and then all we have to do is say that this integrand is bounded in terms of n and t, and that it converges pointwise to f prime at a sub n, which it does, because bn minus an is going to 0. Yeah. I'm pretty sure I also use exactly the same proof. I'm going to use the product topology of I'm going to use the product topology of n overline times 0, 1. Is that exactly what I did? Yeah, it's an integration. The answer is I feel like I just scrolled over it 3 times. My scroll wheel is really finicky. Sometimes it doesn't. Okay, it's right here. Yes. Literally exactly the same thing as I was going to do. N overline times the interval 0, 1. This is a compact set. It's literally exactly what I'm going to do. Okay. Excellent. Okay. That's interesting. That's fascinating. These are definitely going to it's basically the same proof again, except we've just used a second sequence instead of a fixed point. It's literally the same proof. Okay. We could probably add it as a corollary even. But we'll just do it normally for now, and then I'll figure out how to fit it somewhere a little better in when I get around to editing all of these. It's literally the same proof. It's exactly the same proof. Okay, so we're up here. So we have this limit, blah blah. Okay, and then we can say we can consider. Let me actually add it to do here. Okay, so we can consider the function g mapping overline n times 0, 1 as being g of we have n comma t, and so you can say if we label a infinity equals b infinity equals x, we can consider this function as being and t equaling, and we just have this. F prime an plus t bn minus an. Okay, and then we could say since g is continuous, continuous on a compact domain, then its image is compact and thus bounded, and moreover, as n goes to infinity, we have f prime a sub n, actually we can just say g, g of n comma t going to f prime at my brain stopped working. F prime at x, by dominated convergence. We honestly don't even need to do this by contradiction. F's differentiable, blah, blah, this term quotient always defined, prove that it converges. We say, take any sequence a(n), bn going to x, having these going to there, and then we can say since f is an antiderivative for the continuous f prime, it's also an indefinite integral function, and then we have this whole deal. And then we can say label a infinity equals b infinity equals x, and consider g g as being this function. G is continuous on a compact domain, so it measures compact and is bounded, and moreover, as n goes to infinity, gnt goes to f prime x. So by dominated convergence, we have the conclusion, and that conclusion is just all of this, and then we just take this limit. So we have limit as n goes to infinity of this thing is equal to this limit as n goes to infinity, which is just the integral 0 to 1 of our limit f prime at x dt, which is just f prime at x, since we just pull it out and the integral is 1. And that's it. And that's that. Okay. Hi, question mark. Okay, so we have this. So we're definitely going to merge this with our earlier theorem. It's literally exactly the same proof, except we've just taken 2 sequences instead of 1. Okay. So as a corollary to this, we can say let f map, I don't know, it might be because you're not logged in. So we can say let f map s to a, okay, so let's set s set to, whoops, a, b, locally convex, and f map s to a, b, continuously differentiable, then f is locally injective. That's not what I want to say. Continuously differentiable with f prime at x0 not 0. Then f is locally yes, f is locally injective. Okay. And the proof is kind of immediate, so we can just say, suppose not, then we can find sequences a sub n, b sub n, actually we can say, yeah, a sub n going to b sub n, a sub n, b sub n going to x0, with an not bn, but f of a sub n equaling f b sub n, but then we have f at a sub n minus f b sub n divided by a sub n minus b sub n. This is just 0, and this goes to f prime at x0. And that's it. Okay, so that's nice. I definitely want to fit this in with the other theorem for sure. This is like a lot of text that doesn't need to be here. Again. But I'll just leave that there. Okay, so now we want to say, so we've got this condition. So we've got this locally injective. So that's our first piece of proving this inverse function theorem. The next thing we want to prove, let's reanalyze this proof here. The next thing we want to prove is that, so we have a local inverse. That's actually what we have so far. And we want to prove that this function is continuous and differentiable itself. Interesting. Oh, they're just using more of these inequalities. Interesting. Okay, so they're also using, in order to prove C1, they're proving that if they're going to decompose G is, at y plus k is x plus h. So h is sort of the offset. So f at x plus h is f at x plus k. Does that make sense? Yes, it does. If y is f of x. Okay. C1. We can maybe try to approach this. Okay. Let's try, not this one. Let's try, in this theorem, we can say, instead of saying f prime at x0 is an A star, Did Dr. Sun, are they doing their thing that you wanted to go to, by the way? No idea? Yeah. Well, that's okay. Okay. So because we've done this first part really differently from the way they've done this, in order to prove this, they're using their inequalities again. Actually, our proof is actually really nice. For a continuously differentiable function being locally injective. That's actually this is actually a really nice proof. The thing that I like about this is that it's almost purely topological, with the exception of like we don't have to do any estimations actually. It's kind of nice how that ends up being. The problem, though, is that now it's really hard to prove. It's really hard to prove what we want to do. There might be a lot, actually, that we need to do. There might be a lot, now that I'm thinking about it. One of the questions I have, actually, about how we're going to do this going forward is, so eventually, so we've proven this locally injective condition. This essentially proves, this one. This essentially proves that we have a local inverse function. The rest of our results in regards to the inverse function theorem is essentially just proving increasing degrees of smoothness. So for this simple case, we just want to show that there is a that its inverse function is continuously differentiable. But as we sort of increase in the smoothness, so for example, if we increase f, if we upgrade that to analytic, or for example, if we say, let's say S is a proper domain, how do we know what kinds of conditions the image set will have? Actually, this is a solvable problem. I think it's possible if we have I think it's possible to say that if we have a, what I want to say is that the analytic image of a proper domain is another proper domain. I don't know if that's true if we have actually, no, it might not be convex. I think actually no, that's definitely true, or rather, what I had just said is not true. So what I wanted to say is that the image of a simple domain is the image of a proper domain is a proper domain. That's false. Actually, there are. I think it's false. I think I should be able to come up with a counterexample for that. Or maybe not. Maybe I'm actually just totally wrong. Okay, well, we've got this much, that's fine. Let me consult what I had done previously, because we do have an actual proof that works in this space. It's just not good. It seems like, so in my previous draft we did do the same thing. So we did prove that, right, if we have a function continuously differentiable with a non-zero derivative, then it's locally one-to-one. We have this other lemma here. I'm not sure what this lemma is for. Let me see. Okay. I think the lemma is for this theorem, which is this theorem that we had tried to prove, or that we had proven in our paper, is that if we have a function which is continuously differentiable in an open set, which an open set in our set, every open set is a proper domain, but a continuously differentiable function in an open set has this property that it is not an open mapping. Is essentially what this other theorem had said. So it's a negative result about open mappings. That if it's not an open mapping if its derivative is not a unit. We could just as easily demonstrate that if we have a function whose derivative is not a unit, we could just as easily demonstrate that there's no possible way that it could have a differentiable inverse function. So we do have that it's locally one-to-one, it's locally invertible. That we've just proven that, so long as the derivative is non-zero. But we also have that this condition, if its derivative is not a unit, it can't be differentiable, but also it's going to not be an open mapping. This doesn't apply necessarily, or rather, this is meaningless in the context of more abstract domains. So we have sort of abstractionized our domains to the point where they only have to be convex or locally convex, and with usually some other properties. But usually the vast majority of other than our analyticity theorem, every other theorem uses locally convex. Just about every other theorem it applies to every set which is locally convex. The only time I think that we don't have that the only time we don't have this is not this. Oh, okay. This condition here is required. Is that the compact convergence of differentiable functions is differentiable. That one and the analyticity. I'm very convinced that analyticity is not possible for general In fact, well, we know it's not possible for general locally convex sets, because it's not true just on the real line, and the real line is a convex set, as an example. In order to prove this, so this is the only other one that we'd have. I think it might be possible to prove this without utilizing this this condition. So if we have all these integrals tending to 0, we could alternatively try to change this. So for here, this applies for simply connected proper domains, and it's suggesting if we have, let's see, oh yes, okay, this might not be true on a not proper domain either, actually. So we could replace analytic with differentiable. To make this more accessible. But if we did that, I think this essential result, no, because this is still true. What isn't true is that if we have a vanishing integral on a loop, even in a simply connected set, this doesn't necessarily prove our function is even differentiable. It does prove that our function has an antiderivative, but having an antiderivative doesn't prove differentiability in the general case. If we have a locally convex set, then this would prove that we have an antiderivative, I believe, or at least a local antiderivative, if it's locally convex and simply connected. Okay. This proof doesn't do that, though. This could possibly be updated. I'll leave this as it is, though. Actually, I'll make a note to generalize this as well. I feel like this should be true even off a proper domain, that compact convergence of differentiable functions is differentiable. Maybe if we require continuously differentiable or something. But if we have proper domain, that restriction doesn't do anything. That's a non-restriction, so it would be strictly more general. Okay, I'll just leave this there. But yes, almost all of our results apply to locally convex sets, or convex sets sometimes, if we're doing sort of a limited, easier version. So any result like this shouldn't require anything having to do with, any result like this shouldn't have anything to do with proper domains, I think, if we're excluding analyticity. And given that almost all of our results apply to locally convex sets, we should probably want to expect the same thing happens here. So I was thinking before that I'm not sure whether or not, I actually just thought of a counterexample. But I was thinking before, I wasn't sure that if we had a proper domain and we put it through the image, we took its image under an analytic function, and let's say, just for the sake of simplicity, with a derivative which is a unit. I was unsure if the image would also be I was unsure if the image would also be a proper domain. However, I have a negative result, which is that even if we have even an analytic image of a locally convex set, or even a convex set, will usually not be locally convex or convex. Actually, we can actually put a very strong bound of a very strong negative result, saying that there are convex sets and analytic functions for which the image of that convex set has no non-singular convex subsets. And the essential proof of that, so this would be sort of a restriction on sometimes if we want to try to approach this idea of inverse function being differentiable, we might not end up with a locally convex domain. We might not end up with a locally convex domain. And the essential idea for that is, just take the complex plane, and just take a straight line like this or something. Actually, it would be easier if we did, a straight line. If you take a straight line and take the image of, and so this line is, so this will be the real axis. This will be the imaginary axis. And actually we'll say, hold on. We'll give her a straight line. So this will be our set. It's just the straight line. This is a convex set. It's just a line segment. But if you take its image through the exponential function, you're actually going to get something along the lines of something like this, or something. An exponential curve, a spiral. Yeah, and there's no convex subsets except for singleton points. That's sort of a limiting. That's something that's pretty limiting, I think. Is that that sometimes we can have even a very nice convex set, and we take its image, and it'll end up being a very not nice set like this. So for example, one of the ideas I wanted to use is locally convex sets are really nice, since just like we did here, we had used the fact that we're in a convex set to identify that the difference quotient is always defined. That's something that we had used. We wouldn't be able to do that. So once we get our inverse function, so we have this locally injective property. Once we get our inverse function, we're not going to be able to use this property. We're not going to be able to use any locally convex property, in fact, at all. In fact, we might not even have any convex subsets of the domain of the inverse function. So proving differentiability is actually going to be really difficult. There are some positive results though that we can use. So we can say, so we'll say, since f is locally injective, let G, we can say we can find a neighborhood we'll say x0 is in this neighborhood U, which is subset to the this domain S, and inverse function G mapping U to A with G is F inverse over U. And also G inverse of X is F of x over, I don't know, x near x0, something like this. So something we can say is, since we have f prime at x0 is in A star, what we want to say is it should be possible to select a neighborhood restrictive enough such that what we actually want to say is that every difference quotient we'll have this fraction fa minus fb over a minus b is in A star. So this is sort of rough. This isn't quite a proof. This isn't even the kind of language I would usually use in a proof. But sort of roughly, what we can say is that because we have this continuously differentiable function, so we get this inverse function. We don't know if it's continuous or differentiable or anything, but we have a local inverse function, and we want to say, since our function has a derivative which is a unit, and because it's continuously differentiable, so that we can take these limits like this, there should be a neighborhood where any of these difference quotients between a and b are also units. So we should be able to choose this neighborhood. But then just by applying g, and just by applying g as the inverse function of f, we do end up with a condition that this difference quotient is just the reciprocal of the difference quotient for g. So that's one of the things that we can do. Yeah, this usually how the proofs are. Yeah, at first, definitely very, very unclear and lazy at first. Yeah, so what we want to say is that oh, actually, I think I know exactly how to do this. I just realized this implication here, that S subset A be convex and F be continuously differentiable. Then we have this F prime is this. This implication can actually go the other way. If we can calculate f prime using this limit, if this can be calculated this way, I think actually in the reverse direction we don't need this convex condition. But if we can calculate it this way in reverse, we can actually say that f has to be continuously differentiable. That actually is going to be really useful for us. I just realized what we can do here. So what we can actually do is, so we can find this neighborhood, so f is locally injective, we find this neighborhood over which f is injective, and since S is locally convex, we may assume also that U is convex. So we're going to say, we're going to pick a convex subset where f is continuously differentiable, and then we can say this gives us an inverse function g mapping the image f of u to u having g inverse equals f restricted to u. And then we can just prove, so we can say, now take any a sub n and b sub n going to, actually let's pick, take any x in the set f of u and any sequences a and bn going to x, actually we'll label this y instead of x because it's inverse, such that a sub n is not b sub n for any n. Then we can just label, so this is the first part. So f is locally injective, we have this neighborhood blah blah over which f is locally injective, so we have this neighborhood over which f is injective. And since S is locally convex, we may assume also that U is convex. So we have this inverse function, take any y in f of U, and a and bn going to y, such that an is not equal to bn for any n. And then we can say, now we have, so we have this, we have, let's say, we can say C sub n is, we can let C sub n be, sorry, A sub n and B sub n are in f of U. Okay, so now take any f and y of U, and b and go into y within f of U, such that so on and so forth. Now we can take, so okay, so A and B are in f of U, which means we can apply f inverse to an and bn to get some other sequences, cn and dn. Instead of f inverse, these would be G, or alternatively we can apply f inverse dn, sorry, f of dn and f of cn. Okay. Yeah, let's do it this way. Okay. Okay, so what we want to identify is that essentially we want to show, we want to use, I think, how will we do that? Essentially, I want to, so if we assume that G is continuous, which it isn't, I mean it is, but we don't know that yet. If we assume G is continuous, this actually this actually gives us the result really quickly. So if we assume G is continuous, if we assume G is continuous, then this actually gives us, we have f at Cn minus f at dn divided by Cn minus dn. This difference quotient is just Cn minus dn over G, sorry, an minus bn over G of an minus G of bn. So this is sort of what we're going for. Is that we just want to take, we just want to basically do a change of variables, which implicitly gives us the reciprocal of this difference quotient. Since this is a unit, we should have its inverse. Since if we have Cn and Dn going to G of y, yeah. So if we assume G is continuous, then we have Cn and Dn going to G of y. And something like this. This is sort of the idea that we want to get at. We're saying we want to say this reciprocal is valid if we have Cn and Dn limiting to g of y, which would sort of imply that g is continuous. That would require, I think that's maybe possible. I'm not sure. If we do have this continuity, this essentially does work, though. This sort of idea that we're getting at. So we want to say if g is continuous, if we try to take this limit, right, this limit of g of an minus g of bn over an minus bn, if we take this limit, these g of an if we take this g, then we end up with these Cn and Dn, and this gives us essentially a way to calculate the derivative for f. And if we can calculate this derivative for f, then we can also calculate this derivative for g. That's essentially what we want to say. And also it gives us this reciprocal condition, which is nice. But doing this requires the inverse function to be continuous, and I'm actually not 100% sure on how I would do that. I'm not 100% sure on that one. Let's look at maybe that. No, that won't work here. So proving the open mapping condition is actually going to be really difficult for us. The problem with proving that the inverse is continuous is that we essentially have to prove that Actually, I remember having to solve this problem before, albeit in a much worse way. Proving that, essentially proving that if we have a convergent sequence, that it converges, that it's a convergent sequence in the image, we want to also be a convergent sequence in the in the when we take its pre-image. So we take when we apply g, the inverse function. But that okay, well, as promised, I really have no idea what I'm doing. But I think to not have this just totally grind to a halt, let's do something more productive, which is I'm going to attempt to integrate this theorem. I'm going to attempt to integrate this to, or rather, this theorem, something like this. I'm going to attempt to integrate this into the earlier theorem that we had identified as being sort of a simpler version of this. So let's just do that, because that's something that we can do right now, rather than just sort of sitting here flailing. This is power series, should be all the way up in the integration section. I think, right, this is actually it. Yes. Okay, so let's put, we have a lot of theorems here that actually I don't want to mess with too much, because I like that these fit really nicely, cleanly onto pages. So the theorem that we want to append is this one. So we have a locally convex and without isolated points. Then every indefinite integral function is also an antiderivative. That means it differentiates to, so we have a indefinite integral function is also an antiderivative. Actually, we can maybe go here and then update this as a corollary instead. So this one is saying let these functions be integrable. No, not this one. I'm actually thinking of this one. F being antiderivative and f be integrable over sigma. Then we get this. An antiderivative is an indefinite integral function, like this. So what we had done in the other theorem is we had shown if f is an antiderivative for a continuous function instead of just integrable, continuous, then this function will be locally injective. That would be what we would be doing. Okay, I think we'll take our other theorem and we will put it probably just here at the end of all of this. And we will just add a note that the proof is similar to this one. Yes, I'm gonna tag this. I'm gonna give it a label. Okay, I'm just going to copy sort of what we did here. This and this theorem and its corollary and the next theorem that we're working on. We'll have to redo part of this theorem to prove analyticity. I think actually it is possible, I think, to prove the inverse, to prove that the analytic image of a proper domain is also a proper domain. I think it's still possible to do that. So long as it's locally convex, maybe? So long as the image is locally convex. We'll see how that goes. We could also, well, I'll just think about it. I'll just think on that. So let's put this back up in integration. That's down here. Okay. Okay, so okay, so we'll say say, okay, so since f is an antiderivative for the continuous f prime in the convex set S, it is also an indefinite integral function, and by repeating, okay, so we can say, okay, take any sequence n and b going to x having and not equal to bn, since f is an antiderivative for the continuous f prime in the convex set S, it's also an indefinite integral function. And then we can say, by repeating some work from, and then we'll reference this proof. This proof was the one that we want to essentially reference is this one. Okay, where were we? Yes, we were right here. Okay, so I'm choosing by one, image convex is bounded. Okay. And the corollary S subset A, B locally convex. Change the differentiable, F prime, x is non-zero, F is locally injective. Near x 0. Okay, so we've integrated these a little bit. Okay. So we have this here. This actually fits really nicely in this spot because of this fits nicely in this spot since we have all these other theorems about locally convex sets and differentiable functions on locally convex sets. So this actually goes pretty nicely in this spot. This is a lot of theorems for one section in comparison to the other sections. Like section 5 only has 8 theorems. And we're sort of like on our 15th. Same for analyticity actually. Or I guess maybe differentiability is just really short. Okay, well anyway. Okay, so we have these. All I want to do now, the only thing I want to do at the moment, we can get to proving the inverses are analytic. All I want to do is prove these inverse functions. So we have the inverse is if the derivative is non-zero, then we have a it's locally there's a neighborhood over which it's injective if the derivative is non-zero. I think the only thing I want to do is prove that that the inverse function is continuous, given that the derivative that it exists and that the derivative is non-zero. So f is continuously differentiable, and I want to show that there's this there's a neighborhood where this inverse function is continuous. If we have that, so if we have it's continuous and also the derivative is a unit, then we can prove that this inverse function theorem, that it's differentiable. In fact, we can prove that it's if we have a continuously differentiable function, that it has its inverse function is it exists and is differentiable if and only if the derivative is a unit. So I think what we're going to do is we're just going to try to prove that given that we have continuously differentiable, f prime is non-zero, then we have this so it's injective and this inverse function is continuous. That's all I want to do right now. So we're going to do that. So we're going to say let S subset to A be, actually we'll probably merge this with this corollary, but I'll just leave it like this for now. So be locally convex and F map S to A be continuously differentiable with F prime X 0 is non-zero, and there is f has a continuous local inverse function near x0. Okay, so we already have that it's injective on a neighborhood. I think what we want to do is we want to restrict this neighborhood to be small enough we want to restrict the neighborhood to be small enough so that if we have some sequence approaching in the image approaching f of x0, we want to say that essentially we want to restrict this image to be small enough that we don't have any any points on sort of the boundary of the domain of this neighborhood. Yes. Okay, so how are we going to do that? So we want to take not only a neighborhood that's small enough to be injective, but also small enough that it's not just barely injective. We want it to be small enough that that it's impossible to approach a point which would force it to not be injective. So how can we do that? So normally if we were, oh yeah, a very good proof, ASDF. If we were just using, so we can try to think about this as if we're just using, if we're just using a real or complex valued function, we could just say, oh wait, I think I know what we want. We want it to be such that that there's no point on the boundary where, so we want it to be such that if we subtract any point, there's no point on the boundary which too closely approximates that point. Essentially, that there's no sequence that just sort of leaves the space. So we could try to have it. Maybe this. Oh gosh, this is actually very difficult. Okay, I think I know what to do. I think I actually know what to do. So we only need it to be, so it needs to be injective, yes. But it needs to be such that if we have a sequence approaching, a sequence in the image, so we want to have a neighborhood of x0, we want that neighborhood to be such that if we take the image of that neighborhood over f, that we don't have a sequence in the image approaching the image of x0, but for which the preimage does not approach x0. But the way to do that, so if we want to force non-convergence, the only thing actually that we need is to have okay, yes, okay, I have an idea. Okay, I know what to do. It only needs to be restricted on a single index. Okay, so we'll say let k be in n0 in n be equal to, actually we'll just say let k equal to z of f prime and x0, which is in naturals. So we'll say, so take an index k, which is here, and then we'll say, and actually we'll first say, let u x0 in u subset to s be our neighborhood over which f is injective. Sure, whatever. And then we can say let k be z of f prime at x0. Then we can say, consider that the projection p sub k composed with f, actually f prime, yes, is continuous. So essentially what we want to do is, we know f prime at x0 is non-zero, so we're going to find one of the indices, one of the indices where it's non-zero, and then we're going to restrict f prime to be in a position where there's no possible way that we can end up with an overlap, basically. We just want there to be no way to get an overlap. So we'll say let f k be in this thing. Consider that the projection pk f prime is continuous. So we should have and we'll call this O as being equal to the set of x in S such that p sub k of f prime and x, if we take the difference between this, and actually we'll say this and x pk at, actually we'll just do this, f prime and x0, is, so this difference is less than p sub k f prime at x0 as a subset S as a relative open set. So essentially we're taking the preimage. So we have this continuous function, and we're taking this preimage of we're taking a preimage of an open set of this continuous function. This is really messy, but essentially what we want to say is actually we'll just say the function pk f prime at x minus f prime at x0 is continuous. And so we're just saying, we're just taking this preimage. Okay, this is really messy, but what we're doing is we've got, so our derivative is non-zero. Because the derivative is non-zero, there's some index where it's not zero, and so we're going to take the smallest index where it's not zero. That'll be our k. And because we have f prime is continuous, this whole function here, so we take the projection of f prime minus x prime at x0, so x prime at x0, that's a constant. pk projection, that's continuous. F prime, that's continuous. So this whole thing is continuous. So we should have this relative open set, and actually we can say we actually want the absolute value of this pk is continuous. So we should have this relative open set where this absolute value of this pk is being strictly less than pk of f prime x0 divided by 2. So this is a relative open set. And it also has x0 is in this open set. So if this is actually, I think, this is going to be enough to as long as we restrict our inverse function to sort of be in both u, where it's locally invertible, locally injective, and also in O, we should be able to prove that within O, if we take a convex subset of the intersection O with U, then we actually should have a set where we should have a set where f prime we should have a set where the projection p sub k of f prime is I'm gonna develop words eventually, where pk of f prime is also injective. Actually injective in a more strong sense, in that it should be, in any given direction, it should be monotone. So there should be no way to approach some direction without this just increasing. So this difference essentially would be increasing as we go away from x0. That's essentially what we want to say. So then we can say okay, since f is locally injective, actually we can say locally injective, and S is locally convex, we can find a neighborhood X in U subset to O, over which, actually, it's not even required to do that. Huh, maybe this proof is actually stronger. Okay. Actually, so we don't need this. So since S is locally convex, we can find a convex neighborhood x0 in S, in U, subset to O, which is in turn subset to S. And then I think actually we can, no, actually we still need an F being injective. We still need that. Okay. So we've got our K and so on. We have a relative open set and so on, yes. Actually, now that I think of it, yeah, maybe this is a problem. So this only gives us no, this is fine, I think. So we're not going to prove that the F prime, PKF prime is, well, actually, yeah, no. We're not going to prove that PKF prime is injective, but given that PKF prime is now, its a difference between that and F prime x0 it's very close to F prime x0. I think we can use this to make some estimations with integration. We'll figure out how that goes. So we find this convex neighborhood. Okay, so now what we can say is since F is injective over U, we can let G map F of U to U be its inverse function, be the inverse function over its image. Okay, now we, oops, oh gosh. Now we just have to prove that it is continuous. Okay, so by contradiction, suppose not, then we have a sequence actually, let me think on that. Okay. Let A, okay, so we're going to take a sequence, let A be in the image, have limit A sub n goes to y, then we can let, let's say, actually we'll say let y sub n be this limit. Then we can let x sub n be equal to g of y sub n, and we need only prove that x sub n goes to x which is equal to g of y. Okay. So this is what we're going to prove. And so we'll say, so what we want to show is we'll say, okay, so since we have f of x sub n going to f of x, we can consider something like f at x minus f at x sub n is equal to the integral, and we'll have from x to xn, or sorry, xn to x. Actually, it doesn't matter. We'll do xn first. Xn minus x. X to xn of f prime of f prime of oh gosh, I'll just do z d z. But then we can just do substitution. This will be x sub n minus x times the integral 0 to 1 of f prime, and we have x plus x sub n minus x times t dt, I think. Okay, what we want to do right here is we're going to show that we're going to say, suppose that x sub n does not converge to x by contradiction. And if that happens, then there has to be, so this difference, xn minus x, can't converge to 0. We're going to find an index where it doesn't converge to 0, and we're going to evaluate this whole thing on the projection of whatever this index is, where this is not going to 0, multiplied by k, which is z of f prime x, 0. And then we're going to find out that this can't tend to 0. That's the plan. That's sort of what we're going to. Okay, so we'll say, okay, so we have k, z, f prime, blah blah. We have this open set having this. F is locally injective. As convex, we find convex neighborhood this, over which f is injective. Since f is injective over v, we can let g be the inverse function over its image. Let yn have this limit. Then we can let xn be gyn. We can only prove that this. Okay. And then, okay, so by contradiction, suppose that x of n does not go to x, then let j be the element infimum over all n of z of, actually we'll just say let j in n be the least index over which p sub j of xn minus x fails to converge to 0. So that's what we're going to say. Then we have p sub jk of fxn minus fx. This is a sum across ordered pairs AB equals JK of, we have P sub A xn minus x, P sub B of the integral. Actually, we can just pull this through. Integral 0 to 1. Actually, let's put this, no, this is fine. Integral 0 to 1 of, we have P sub B of f prime x plus x sub n minus x t dt. Okay. Okay, so what we're going to end up doing, so we know that this this integral, we want to say, oh, maybe this is important. We might need our xn's to be bounded. Or no, actually no. It's enough, I think, for this. It's enough for actually this to be bounded. Actually, I don't know if we'll have that either. We might need our xn to be bounded. It might need to be bounded on that's maybe important. Okay, so we have this summation AB equals JK. What I want to say is, oh, I know. This whole integral. Oh no, that's not quite right. We have okay. On all of the indices lower than k, f prime is going to tend to 0 as we approach x0. We don't know xn is approaching x0. So that doesn't help us at all. That doesn't help us at all. Actually, no, that's not necessary. We know that this f prime is bounded. It's bounded in a neighborhood of f prime of x on its pk. We don't know about the rest of them. But at the very least, gosh. Okay, I'm gonna have to think about this one more. That's okay. I'm actually, so I do know that this theorem will apply if our function is analytic. We still have just a really awful proof for this in our draft. But I would like to try to work out this more elegant proof. I'm going to think on this one a little more. We do at least have some proof sketch for once we figure out this continuity condition, we will end up with having the inverse function theorem proper, for at least for continuously differentiable functions. And then we will just have to prove that a differentiable image of a proper domain is another proper domain. And then once we have that, we will have sort of what we need. Actually, we may not need that. We could probably ignore the locally convex condition. Actually, possibly, maybe. But in any case, I'm going to. We will. I think stop there for today. I'll think on this one a little more. I'll try to figure out exactly how I want to work this out. The direction I'm sort of heading in is I want to try to show that for the pairs A and B, which are not just equal to A, and A is J and B is K, for all of these pairs, or I guess it's the other way around. For all of these pairs, yeah. For all of these pairs which don't end up like this, what we want to try to prove is that is that these terms do actually converge. That's sort of what we want to show. I'm not sure how exactly that's going to work out. I think if we have xn being bounded, then that's actually sufficient. But I'm not entirely sure. All we know is that if A is actually, I think we do need J, JK. All we know is that if A is less than J, then this will converge to 0. And also, if A is less than J, so if A is less than J, this will converge to 0. Oh no, we don't get that. If A is less than J, if A is less than J, we get this converging to 0. And if B is less than K, then this will converge to 0. I think. Yes. No. Maybe. I don't know. That's sort of what we want to get at, is that this will converge to 0 as well. All we need to prove is that there's some index where they don't agree on. That's sort of the goal. I'll analyze this a little more. I think maybe not exactly the way I've set it up with these J's and K's, but I think something along the lines of what we're doing here is probably what we want. Something along these lines. So I'll try to figure out how to make this work a little better. But until then, thank you for joining me. I hope you had a little bit of fun, at least trying to think about these ideas and trying to work out maybe what we'll do. Yes, but I will be back tomorrow as always. And thank you very much for watching. See you next time. Thank you very much. I'm glad you enjoyed yourself.